there is an organization in astronomy, amateur astronomy, called the Association of Lunar and Planetary Observer, also known as ALPO. Within that group, is the study of the solar system bodies by amateur astronomer. Now, within that group, it divides to many sessions, like the Mercury session, which I'm the coordinator, and you have Venus session, you got the lunar session, you got Mars session, and Jupiter session, Saturn session, and you have the remote session, the remote planet session, which consists of Uranus and Neptune. And I'm going to include that in Pluto too, right? Even though Pluto's not a planet, but I include Pluto also. And in addition to that, they have other sessions like the minor planet session, which is the asteroids. They have Aurora session. You have a comet session. You got a meteor session. You got a meteorite session, and also they have the solar session. Now, the solar session was established in 1982 by Richard Hill. I'm pretty sure familiar with Richard Hill. He gave out the talk at the visual meeting a couple of years ago, 2-3 years ago. We talked about the sun. And so he established the session. As a matter of fact, he is still the solar session coordinator after 42 years. Wow. So it's very well organized. People that contribute a lot of solar observatory, solar observations, drawings, sunspot numbers, images of white light, H-alpha light, calcium light, you name it. Everything goes to the session. Then he writes about it and report it to the journal. Now, the way it works, it goes by rotation instead of by yearly. The rotation, they go by Carrington number. Carrington number was established by Richard Carrington back in 1859. And he started from rotation 1, 2, 3, 4, and so on. Now we're up to 2287 rotation number. So he reported every rotation period. So not like a yearly paper, like I do with the Mercury session. So anyway, yeah, I thought it's very well organized, and we have a lot of people handing in the solar session there. Okay. We all know that our sun is an amazing star. Our sun is very important to us because it's the only star in the universe that we can study up close. Okay, what are the advantages and disadvantages of observing the sun? Okay, well, we can break that down. Okay, let's list the advantages first. Observation can be done in daylight. We all know that we can see the sun during the day. You don't lose any sleep. Especially, it's good for the elderly. You need a lot of sleep and can't afford to stay up all night, late at night. So it's very convenient for them to observe the sun during the day. There's plenty of light to deal with. You can observe the sun in your yard, your front yard, backyard. You don't have to go anywhere to see it. No need to escape light pollution. Yeah, so it's very convenient. You can do it from your own backyard, something like that. You don't need a mountain telescope. You don't need a gigantic 14-inch or 32-inch like John has. You don't need that. You need maybe something like a small telescope. It's just fine. If you have a 60-millimeter refractor or 70, 80 millimeters or a small reflector, something like that, that's fine. That collects plenty of light. The sun is constantly changing. If you look at the sun one day, it will look different the next day, or the sun looked different from the day before. The sun never looked the same as the day before. I just mentioned that. All right, next, and most importantly, everybody know what that is? Oh, okay. No mosquitoes. Yeah, no mosquitoes. So I know it's very annoying if you do deep sky observing late at night. You get bitten by the mosquito, but during the day, if you observe the sun, you don't deal with this thing. So that's one of the advantages. All right. Disadvantages. Yeah, there's some disadvantages about observing the sun. The sun causes blindness if you're not careful. Okay, first thing first, make sure that everything is safely before you observe the sun. If you have a filter, make sure it's securely on the telescope. Make sure that it's not loose. If it's on the windy day, make sure it's tight. If you have the filter that goes in front of the telescope, make sure it's security. And you know, you don't want to leave unattended with the people around. You never know, it might slide off the filter, so that can be very dangerous. So regardless, always make sure it is safely before you do the solar observing. So, so you might get hot, of course, like today, how hot it was. And if you do solar observing, I'm pretty sure you're going to be very hot. You know, no, the sun is hot, hot, hot. You might get sunburn. I had sunburn once on my forehead and all. You will run to atmospheric disturbances. You know, when the sun gets high in the sky, the heat builds up, and then you start to get turbulence. In order the seeing condition might deteriorate it. The cloud may build up during the day because of the heat convection, and you know, it's nice and clear in the morning, so that's the best time to observe. But if you wait till, you know, like maybe toward noon or something like that, when the sun is high in the sky, then you have a cloud build up. And of course, you have the wind pick up too. The narrow band filter may be quite expensive. Now, I don't want to go too much detail about it, but if you have an H alpha filter or calcium light, it can get very expensive. And if you have a white light, which is inexpensive, and most people can, you know, within the budget, most people can use white light filter to observe the sun, and there's plenty of things to see. And I will show that as I go on. Okay, a little details. You know, the sun goes through the cycle. You know, you have up and down period. You have to say one time, you know, the sun can be very active, and another year the sun can be not too active. Well, during the solar maximum, we find a lot of sunspot numbers. Most of the time, you see the sunspots groups on the high latitude of the sun. Then gradually, as the cycle progresses, it gets closer to the equatorial region. And then that can cause the solar minimum. That's when the new cycle starts at the solar minimum, and you very few sunspots along the equatorial region. Then when the new cycle starts, it starts up here as it goes toward the solar maximum. So now the next slide I want to show you that currently we're on cycle 25. It's the good news. It's much faster than we thought. During the solar minimum, it was back in between 2019 and 2020, and gradually, the line here, this is the prediction of what they thought it would be. Then I can actually see the up and down. These are sunspot numbers going up and down. You can see it's a little above normal, and then it goes high here, then here. This is as of maybe January or February 2024. We have a lot of sunspot numbers in the past few weeks, and back in last spring, so it must be up here. So this was a little lower here, now probably up here somewhere. This is as of February 2024. So hopefully, if the prediction holds, the 2025, it would be the maximum. It would be somewhere around here. That's where you see the maximum number of sunspots and a lot of activities taking place. So let's see what happens. I mean, we still have a year to go before we can witness the maximum activity of the solar cycle. So, and eventually, according to the prediction, if everything holds together, then at sometime after 2026, then you see the slight decrease of the number of sunspots. So, okay, this is the basic setup of the telescope. I used the 8-inch telescope. This is basically how I set it up here. You can see I have a cardboard hood. Excuse me. I have a cardboard here to provide shade as we're looking here. And you can see the H alpha filter here, and you can see the binaural view here. So this is another angle here. So this is basically a setup when I do the solar observing. So this was basically nothing fancy. It's just a basic setup. There's some people prefer our refractor too, and you have the most direct viewing, and you give a better contrast and all. But with the CA telescope, it provides a very nice view. With that,
White light filter.
yeah, it's one light too. Yeah.
Front of the scope.
Yeah. Yeah. But this is the HA filter right here. Yeah, right here.
The question was,
Yeah.
what's in the front?
Oh, the front, yeah, I don't have the front. It's the filter right over here. It's the 3-inch off acted. Yeah, I'm sorry, I didn't put this in here, but yeah, it's the 3-inch off acted. Yeah. Yeah.
Yeah, it's approximately 60 millimeters across. Yeah. Well, it's an RD 630, so
Yeah.
it's a red filter. It's still.
Yeah, with the white light, then H filter use the 3-inch off acted. It's not a full aperture. Yeah. No. Okay, then if I have to do the imaging, I can take this out and put the camera right here. So. Okay, basic solar research that amateurs can do. Now, since I retire, I spend more time to do solar observation, and I'm getting into more into it to do a little research for the Association of Lunar and Planetary Observers for the solar session. And it gets quite interesting. And you get more detail there. It's just taking the images. Then I look for certain things that I can follow up. And there's some of the images I can show you when what I mean by that. Okay, first at the granulation. Granulation, this is white light. Okay, so a white light filter. If you look carefully, you can see the sun made of very fine grain here. Yeah, this is the lonely sunspots. And during the excellency, during the above average seeing condition, you can able to see the sun is full of very small grain light. Yeah. And this is probably the close-up. That's not a best shot, but just to give you an idea, it's not just blend. You can see a lot of grain around here. Now, this is probably the deepest part of the solar atmosphere in white light. This is toward the center, and you're looking at the very big. Now, what it does here, and what I'll show you momentarily, is that I'm going to show you the animation, and you can see it move. And but there's other images I want to show you, a much better shot. All right, this is the close-up of the granulation. I don't know how, not a best shot, but you can see it got a little different shape there, but I have another better shot coming yet. It's very difficult because you need a high resolution. I used a Barlow lens to double in the magnification, and it had to be in good seeing. Then you can able to see the granule. Each granule is like cells. They have different shape. They have polygons. They got irregular shape. Some are almost round. Some got irregular shape again. So the next image is going to show you. Maybe it's a little better. And this is another time. You can see the granulation here. And if you look at close up, you can see they have all different different shape there. So now what is the granulation is, if you ever see like a pot of water being boiled and you look out and you can see it bubbling on the top. Okay, there. So it works the same way, but in very slow motion. The heat is radiated from the center of the sun and using convection, and it's transmit the heat until the photosphere. The photosphere is the light that we see, and you can see it bubbling up in very slow motion. One cell born, then the other one that died. They go one top of another. They come and go, and it's just a matter of a few minutes. One cell lived for maybe for a few minutes, and then it died. Another one come on one top of another. So it's moving very rapidly, but in slow motion. So. Okay, here's another shot here. I think that's the best shot of the granulation up to now, but I'm still working on it. I'm just waiting for the good scene. And you can see some different shape here. Like they have like lanes, they call interlanes here. And you can see all these lanes here and have all this shape here. If you're taking images like every few minutes intervals, you can able to see the motion if you play like in an animation. So, and now we're going to show you the next image, and you can see what I'm talking about. This is so far, this is what I have here, but I'm still working on it, and I'm trying to find a sunspot just like this, and you can see all around here. You can see the very slight motion is moving away from the sunspot, and if you keep an eye on one of it, you can see it's come and go. So, and yeah, you can just see this is 8 o'clock right here. Yeah, you can see this one here. Okay, these are pores. They like sunspot without penumbra. Now this is the umbra, and this is penumbra, and this is all fibrils in here. Yeah, and you can see it's moving out here, and mingled with the outer part of the sunspot, and you can see the motion. Now, if this consists of 9 images from 1511 to 1530, so you're talking about almost 20 minutes. This is 20-minute shot at 9 images. As you can see, everything is pulling out here. So as you can see the motion. So this is one of the best ways to to see how it works around the sunspot there. So the granulation is one of the features that you can observe the sun in white light. Okay, here's the night shot. The white light also. Now what you see here is the Wilson effect. Now, what is the Wilson effect? It was seen by Alexander Wilson back in 1769. He was the first person to notice that when the sunspot is on nearly the edge sun, you can able to see the sunspot has like a saucer shape, and you can see the depth of field. And you can see like the penumbra is a little bit out here and there's a little bit in here. So you can see that the umbra, which is the darker spot of the sunspot, you can see it's a little bit lower than the surrounding area. So it has the depth of field, I want to say here. And now when it's moving to the center of the solar disk, and you can see this flat there, so you don't see the depth of field, but only along the edge. Yeah. Now that's what I call the Wilson effect. Now I did the intensity here. The intensity of this sunspot right here represent this here. You can see outside the penumbra and this side, and the penumbra you can see is much thicker, and here's the umbra, and you can see much thinner here until it become the normal level here. So you can see a little bit on the angle, and you can see the depth of field that the umbra is much below than the surrounding area. So they have the depth of field.
How did you make that graph?
Oh, the software that you can measure the intensity of the image.
Okay.
And I have a line intensity which represent this part of the image.
Wow.
Yeah. This part of the image represent the depth of, and you can see the intensity of the layer here.
Wow.
Yeah. Now you can see here, same thing here. I took the measurement of this image here, and you can see that the penumbra on both sides of the umbra, you can see it even out there. And as you can see, it's much thicker here because you're looking at the angle here. Now, at the close-up shot, you can see what I'm talking about here. You can see this is thicker here, the thicker wall here, and the thinner because you're looking at the edge, and you can see the depth of field. And same thing now it's flat here because it's more toward the center. So this is one of the projects that you can do to study the depth of field on certain sunspots. Okay, filament eruption. All right, now this is with the H-alpha filter, which with isolated certain wavelengths, you can see the hydrogen gas. It's on the measurement on 62, 62, 68. Oh, 68, 62 Armstrong, if I remember correctly. And so what I'm showing here, then you can, that one day I was observing the filament, which is this one right here. This is fully processed, as you can see, you know, the arch way. But on this one here, this is the raw image. This is not processed. This is straight from the image. It's a raw image without any processing, and it looks like this. Okay. Now this is the blue. Now with the H-alpha filter, I can able to calculate it to shift to the blue wing or the red wing of the center line of the H-alpha with the antenna line. Now, when it's on the blue wings, you can able to measure the Doppler effect. When anything that's coming toward us, especially the filament, if it moves, it appears darker. Now, if the filament moves away from us, you can see the redshift, you can see a lot dimmer. No, not like that, brighter. But in this case, the filament was moving toward us on the red wing of the H-alpha center line. It appears a lot dimmer. See the difference? This is blue wing, red wing. Blue wing, that means it's darker, it means closer to us. And when it's the red wing, when it's moving away, it's a lot dimmer. Now, okay, so right away when I was observing, I assumed that, oh, look like it's coming toward us. It's going to be eruption? I don't know yet. But anyway, according to the gong, here, this is from the National Solar Observatory, the website, and you can see this filament, it's the same as this, almost nearly the same time as my image. Now, then I stopped observing. Okay. So about 10 minutes later, you can see it start to move. You see, now it starts to getting, some kind of eruption, and sure enough, it moves out, and now it almost disappears. This is the matter of 10 minutes. So about a couple hours after this image, this filament erupted, shoot up in space. So right away, I knew that that is going to be some kind of eruption in the near future. And sure enough, a few hours later, and it did. So this is one of the things that you can study, the motion of the filaments, whether it's moving or not. If you're on the blue wing, you can see if it's changing the intensity, if it's darker or dimmer, and so forth. And of course, it's the red wings. When any object moving away from us, like in case of the filaments, it's a perfect example. If it's dimmer or brighter, and you can see whether or not the motion is being detected. So this is one of the excellent way, you can do research on the filaments. So, okay, the filament and the parameter connection. Okay, so with the H-alpha filter, when you see the filaments and all, and then you see the parameters. The filament and the parameter are both the same thing, but you see on a different view. When you see a filament on a solar disk through the H-alpha filter, it's appears dark. Okay, same thing like here, the white appears dark because it's a cooler gas and it emits less light. When it emits less light, it appears darker than the surrounding area. Okay, now when it moves to the limb, it becomes the parameters. These parameters here, it's the same thing as the filaments right here. Now, as the sun rotates, it rotates to the limb here, takes about maybe a couple of days, 2-3 days, and after that, it appears the limit. Now, you can see the shape. You can study the change of the shape as it goes on the limb. And of course, you have the disk and the parameter at the same time. And so this is one of the nicest ways you can to see the changes of the filament as it would appear when it's on the limb, if it's survived long enough. So, now the next image, the same thing. It's a nice parameters on the limb. Now, as the sun rotates, and it becomes like this. So this is just a matter of 3 days from when it's on the limb to the on the sun, and you can study how the shape changes at the matter of time. So the filament and the primate connection. This is one of the nicest ways you can do a little research on how the primates and the filament changing as the time go on. Eruption primates. This is one of the nice shot here. If there's a flare on the limb, what I didn't see anything on the limb, probably beyond the limb, and that there was some kind of flare erupted on the far side of the sun, beyond the limb, and caused spray prominence, and there's all the ejected element shooting out. So you assume there was a big flare on that side of the sun, which was beyond the limb. So here's another shot. Now this time you can see some flares here erupted and shoot out the spray prominence there. And it's just, you can actually see slow motion. If you stare out for a few minutes, maybe like 5 minutes, you can able to see the slow motion. So.
Is this a different filter?
No, this is the same filter. This is H alpha filter. So yeah.
So you're shooting this in black and white, right?
Yes.
And coloring.
Yeah. Okay. Yeah. I always shoot in black and white because you got the maximum contrast, and you can deal with the brightness and the contrast much better if you were taking color. The color would be just like a washout. But if you want to have the image more appealing, you can colorize. It's very similar to the color if you were to take with the color images, a color camera. But sometimes I don't like that because it throws off the contrast a little bit. So sometimes it depends. If the black and white image looks good, then I can colorize it. It makes it look more appealing. But I always like black and white because it shows a nice contrast.
Frank, is this a Daystar?
Yes, the daytime filter, yes. Okay, this is just recently, a couple of months ago, I always dreamed to take image of the loop prominence. I've seen some of the loop prominence in the past used. It's almost a half the size of the sun, and just make a nice loop. I have never seen that until that time on June 24th. There was a flare on the sun, which again, beyond the limb. And all of a sudden I see, it wasn't very bright, but if you cover your eyes, I see nice, beautiful, thin thread of prominence. Loop one after the other. You see 2, 3, 4, about 4 loops overlapping, one on top of another. And what a beautiful sight. Visually looked nice though. And oh, let me take a picture right away. But it moved. About an hour later, it just spread out. So I was very happy about this. I mean, I was excited, and finally I imaged the loop prominence. This time is overlapping about four loops, one top of another, instead of one big loop. So.
Great.
Okay, light bridges. Now back to white light. What you see through the white light, sometimes if you have a normal size sunspot group or a small or large sunspot, sometimes you see some kind of lighting event in the umbra. Okay, we don't know too much about the light bridge, how to develop, how the, when you see a sunspot, the umbra, sometimes you see a light crossing the umbra. We don't know how to develop. It may start from one side of the spot, or start on this side, or they meet together. It's very hard to see. It's not a question hard to see, but it's very hard to find out how to form. You got to spend a lot of time on it. Well, in this case, it's a nice group here, which is group number, sunspot 13634. just one day, you see like a light burst right here. It's just like cutting across the umbra here. 24 hours later, and you see dramatically change here. Now this time it's just like just crossing the umbra. So what caused the change from here to here in just 24 hours? How did it develop? All of a sudden, what happened to this bridge over here? Just disappear, and how this form across here? Nobody knows. Not even professional astronomers, they don't spend enough time on this. So this is one of the excellent projects that the amateur astronomer can do. Keep track of the light bursts, which we really don't understand about it. It's not very well understood. And this is one of the excellent projects you can do, especially in white light. There's many things to see and look after it and do a little research. So how the light bursts are formed. Some are very bright, some are very thick and thinner. But check out the next image. That's a little impressive here. Here's one light burst right across here. Beautiful. It's over the sunspot. I don't know. It's over the sunspot, or it's just crossing the the umbra here. And you can see this one here. Now, what's the difference between these two here? Now, if you look carefully, now you see a light burst here. If you look carefully, especially around the outside of the umbra, you can see like a little lighting effect. You see the little light is a little brighter than the surrounding area. Okay, all right. This is one of the parts that they call the outer ring of the spot. But again, that's not very well understood, but they think that the granules are much smaller and given much smaller than the surrounding area, and of course the lanes. This lane here, it's very, very dim and appears brighter all around here. So it's another research that the amateurs can do to keep tracking about the intensity or the brightness. It varies around the outside of the penumbra. So, and you can see how pointed by the arrow here. Yeah. In addition to the light burst too, and the sunspot together. Yeah. So in the near future, when I have time, if I see the light burst, I'm going to keep imaging. If I have time throughout the day, to see if there's any changes, how to develop, or maybe it's breaking apart, or if it started on one side and it started this side, or just crisscross. So that's what it is. A professional astronomer, they don't look at everything. They study the satellite, the corona. They use the satellite data. Then study about the outer corona. That's their, that's their project to do. But the amateur astronomers can do something like this. Okay, a possible wave. Well, I don't know if I thought this in correctly, but if you look at closely at the sunspot, there's some kind of point here. Here's a curve here. It must have broke away from the main umbra here. So they'll call the wave here. Now remember, this is white light. I found this after I processes, and something look like it's broken off here. So I don't know if it's moving out, or it's moving in, or maybe it stays, or it's just breaking apart and move out. I don't know about that. I didn't follow up because I didn't know. But in H-alpha filter, they are kind of waves that called molten wave or alpha wave. When there's some kind of a flare or flash in H-alpha light, and you can see the wave moving away. It's very similar if you throw a rock or pebble in a pond, and you can see the wave moving out. It was something like that, but it's quite rare, and you have to look at the right time, and you got to look at the right time to see if you detect the wave there. But that's very hard to do that. Yeah,
They refer to that as a sunquake.
they call it sound waves.
I've heard sunquake.
Well, they call it sound wave. I don't know about the sunquake. But you're talking about the whole sun. It's vibrating. They call it sunquake. It's vibrating. It's like a bell. It's vibrating.
I'm talking about, like you said, a drop of a pebble in a
Yeah,
pond.
you see the
It
wave,
ripples
yeah.
out.
Yes.
I've
Yeah.
heard it referred both ways.
Yeah, but you see that in H alpha light, but you got to look at the right time, at the right moment to see that, and it's very, very faint. It depends on the wavelength, whether it's on the blue wings or the red wings. The double effect, you can see the most. But it's very, very hard. It's very hard to see that. But I don't know if this wave here, it's similar to what we see in H alpha, but I doubt it very much. So. Okay, to spike them. Now we're back in the H alpha light. If you look at carefully, if you have an H alpha filter, if you look carefully along the edge, you may see something like this, like a burning prairie, and it seems like this. You see one little speck comes up and then shoot out and dies, and another one form right after the other. And in good seeing, you can see a little fuzzy along. This is along the chromosphere layer of the sun. And you can able to see the spikes coming in and out every other minute, and you see the very slow motion. So, but I don't take any more images than that because if I would take maybe several more images after that, then you play back as an animation, you can see the movement. They go like up and down. Yeah. The next one is again. You see all the spikes here along the edge here. When there's an active group here, it seems to be much more thicker, and the spicule is more apparently around the active group. And you can see it's much larger than the previous slide. Of course, there was a flare on the sun along the edge, right over here somewhere, and you see it's just a spike here because the spike prominence, and it just shoot up. They call spray prominence when there's a flare on the edge, they shoot up all the elements, and you can see here there's a spike just shoot up like that. And it's a spicule that's much thicker here. Then if we continue around this side here, you see getting thinner and thinner and thinner. Now the photospheric vacuum. Now back in white light. Now normally when you see a sunspot along the edge, you can see some of vein like some white area around here, and same thing like here, all this here. They call the vacuum. They are much easier to see along the edge of the limb than the center of the limb. The reason is that because when you look at the photosphere, the light that we see, the sun, along the edge, you're looking at the upper part of the photosphere. Now, the upper part of the photosphere is a little cooler and it appears darker. Now, the vacuum itself is much hotter and emit more light, and that's why it's more contrast than if you were to see in the middle of this. So of course you see the vacuums here with the H alpha filters, but you see more than that. But the next one, the same thing. There you can see the vacuum much brighter here than if you were to see in the center here, because the center, this is the deepest part of the photosphere. And then to look toward the edge, you look at the upper part of the photosphere, the light we see the sun, and it's much cooler because it emits less light, and of course it increased the contrast, and you can see the vacuum much better because it emits more heat, more light, and you can be able to see it than the surrounding area. Normally you see around the sunspots and all. Even though without the sunspot, you still see the vacuum here, because even before the sunspot form, you can see the vacuum first, and the sunspot may form. Then after it dies, it's still there. So it lasts for months. Then the spot itself. So that's one of the ways you can find out if you see a vacuum along the side here. It could be the upcoming activity. Maybe the sunspot will form. Evolution. Okay, of the sunspot group 13615. Now, I could able to image And this is white light here, and this is H-alpha light. Now you can see I colorize because it looks more appealing. This is one very interesting sunspot group, 13615 on the eastern limb. Now there's light clusters of spots and all. Then look what happened. As time progresses during the week, you can see how they form. And now it's on the other side of the sun, it's ready to go off the limb. And you can see the development here, how the spot form and how one spot dies, one spot form. And you can see it come and go, and you can see the change and it's almost, well, every other day or something like that. And H-alpha light, you can see the changing of the, any flares here. Not too much flare with capture, but you can see all the detail around it. You can see the change until it comes to the limb. So this is one of the nice ways that the amateur can do to follow the changing of the sunspot. The next one, same thing. This one is more impressive. As you can see along the edge of the sun, when it appears along the eastern limb, and as it goes to the middle of the lip, the middle of the disc, you can see how to develop, compare, see that there's a change. Then it goes on the limb again, ready to go off the limb. Now, this is white light, and this is alpha light, as you can see developing. You can see maybe very bright plays here. They're not flares. I mean, they emit a higher temperature that so that appears more light there. So you can see the changes there. So now again, the next one, evolution 13614 again appears on the eastern limb, and now you can watch developing. That's not a small spot, hasn't changed much. And through the H-alpha filter, it developed night filaments here, the one I was talking about before. And the same thing, it come and goes. You can see the used one here, and then it dies off, then it form again, right here. So this is a nice way to study the surrounding area of this particular sunspot group. Okay, all right, this is the most interesting one, 13664. When it appears on the eastern limb, it's like, no, it didn't look too impressive that time. So look what happened day after day. It formed very nice. Look at this. And the group here, look how they form. You got expanding.
Right.
Yeah.
The date?
Hmm?
The date?
The date? This last May. This is May 3rd, May 5th, May 7th, May 8th, May 11th, May 13th. Yeah. And this is white light, and this is H-alpha light. Now, H-alpha light, we all remember that sunspot group. It produces a lot of flares, sub-flares, major flare. And you can see, well, there was no image of the H-alpha filter at the same time because it didn't look too impressive. Then it expanded, and then it got more interesting, and you can see it's very complex, and you can see it grew here. And these are old flares here, pumping in and out. Look at this one here. This flare here that's popping in and out, and then it's still active along the limb here, and you can see those sprays prominent shooting out from this active group. And we all know that it creates the aurora. Okay, now this is the group here on the Solar Monitor website, and I can able to track the sunspot number. They call region sunspot number, and you can see if any flares occur here. Now these are numbers on sunspots, class, whether it's they have different class here, class spot, size, region, and these are the date. They keep tracking all the sunspots group that's visible at the time you're observing. So this is the top 25 sunspot region for cycle 25. So this is the fourth. The one I just showed you is the fourth largest group so far for cycle 25. So it was pretty impressive there. And of course, this one here, it can be similar to the one of Richard Carrington back in 1859 when it produced one of the major flare on record at that time in 1859 in white light. You can able to see the flare in white light. You can see the flare, the spot here, spot there. This is very similar in size, the number of spots compared to 136.64 region last May. It's very similar here, and it produced numbers of flares, subflare, and the same thing with this. So the size is very similar to this. But the next one, you can see comparing side by side. And again, this is not my image, so just to show you what the size compared to the corresponding Carrington sunspot in 1859, which produced major flares. Then there's a lot of interruption, telephone operator interruption back in 1859, and that they would create a lot of aurora. So this is, again, this is very similar to the one we experienced last May. Now, we all know what we saw last May. It's the aurora, right? All right, this is the first time I see aurora from home. And of course, it's visible all over the United States, even down to Puerto Rico. So this is a very active group. And also you can hear here that it's about 4 o'clock, 4:30 in the morning. It was on a Saturday, May 11th. I remember I went to bed Friday night and it was kind of cloudy. Oh my God. So everybody on the lookout for the aurora. I know some of you went to Sunken Meadow or along the North Shore to get a nice view of the northern sky. But I was home, and then I woke up 4 o'clock in the morning. I don't see anything yet. You know, it was a nice, the sky cleared up. I don't see anything. Then I went back in, and about 10, 15 minutes later, I went outside. There it is. I saw something in the northwest part of the sky. It looked like a shading area. It's hard to see the color, but I saw something there. But this was taking, the image was taken with my cell phone right here. That's all you need. And produce a picture like that. I even pick up stars here. Look at this. This is the Big Dipper. Here's the bolt here. It's the handle. And you ever pick up the double, Archon and Mazar. That's all. I was just about to go in to get my my Nikon 3200 1300D digital camera to bring out. Maybe I would take a better picture than the cell phone, but this is good enough. This is very quick, just hold it steady as possible. And it is beautiful. I mean, I didn't bother to go in to get my my other camera. Anyway, so just to give you an idea that the group that I just showed you before is called the aurora. So, okay. Now, the largest flare, I've been observing the sun for almost 40 years. And I was waiting to see the largest flare that I can witness. So far, the largest flare I ever seen was back in March 1989, 35 years ago. This group here, Carrington rotation, what's here? Yeah, active region 155.95. In March 11th, there was flare erupted. It flare erupted. It was like an explosion. There's a size they call 2B flare, which represents the size of the flare and the brightness. They're called 2B. I think the largest is 4. Now 4B flares, it cover double the size, but this is very, very intense, and this has caused a lot of problems, especially in Quebec, where they with the blackout. It caused a problem with the power grid and all. Then about a half hour later, they were taking 1540 Universal Time, then 1650. So it's about a half hour later, and you can see all the elements shooting out here. As you can see, this sunspot group here. Yeah. Now this is taking film. But in the old days, we're using film. So this is probably the best shot I can take with the film. Again, you can see everything shooting out there. Now, if this will be on the limb, then you see a huge spray prominence shooting out there. That should be, otherwise it would be quite impressive. But you can see that it's just coming out like that. And of course, the Aurora too. And you can see Long Island, which I miss it. I think, Ken, you have an image of,
Yeah, I
The
had a
Aurora,
whole
the
bunch of
89
11 by 14 prints that I
Yeah.
brought in. It was,
yeah, that's the one, that's a flare. Not only that, they produce a lot of flares, and this is just one of it. There was another one the next day, there was the big one yet, the following day. So this is quite impressive visually through the eyepiece and the H alpha filter. Um, So hopefully now with the cycle 25 coming up, hopefully I can see another big flare like that. Okay, now visiting solar observation. Now, I'm pretty sure, you probably, when you travel around, you may visit observatory, solar observatory. So in the near future, if you plan to see observatory, see if you can able to go visiting the solar observatory. So let's just give you an example. When I go visit the observatory, the solar observatory in the past. Now, McMath Pierce Solar Observatory, Cape Peak Observatory in Arizona. So I went to visit there and visited a solar observatory, and the mirrors up here, and what it does, it collects the light from the sun and it reflects down all the way down to the underground here. Now the light beam, the inside is the light beam here. This is about 150-foot high, if I remember correctly. So that's how they are doing. Now I went inside, I went by the side here. Well, this is the diagram. Outside the solar observatory, they have a diagram here. You can see the light beam, but to go all the way down here, I think it reflects down here. There's another one here on the underground, and one down here. It's the big long light beam, and the mirrors up here. I think the size is 1.6 meter, if I remember correctly. So then I went by the front, the main entrance. Yeah, this is a plaque. You can see that it was established dedicated 19. I think it was started in 1962, I believe, if I remember correctly. Anyway, on the side of me, there's the door, and I walk in there, and it's like a lobby. And somebody come out here, oh, you're not allowed to. What, the door was open? No, you're not allowed here. That's for the facility here. That's for the employees. It's not allowed. It's not allowed for the public to come here. Oh, I don't know. There was no sign at all. So they asked me to leave. Okay. If you want to see something like that, on the other side of the solar observatory, there's the door that you can go in, and you can see here, there's a door here. You can open up the door, and what you see is like a hollow area. You can see that's one of the light beam I show you. The light beam coming down here. Okay, this is up here. This is the mirror here. This is overexposed here. And what it does is the light beam comes down. Now I don't remember if there was the sunlight coming through here. Maybe they're not doing it at that time. So that's what it looks like. It's just one big hollow, and once you go in there, there's like a little, where you can see here, they got bars around, and you can able to see looking up and look down. Look down would look pretty dark, and I don't know if I took a picture here, and that's what it looked like. So as you can see here, the light beam here. Oh, this is the track here. I don't know. So it's really nothing to see. It's just one big hollow tube. That's when the sunlight goes through. But anyway,
that's now closed. They shut down the McMath because of the new scope in.
yeah, I think so. Yeah, this was about 10 years ago. Yeah, I think they changed the name too, or something like that. But yeah, I think they renovated or they closed down. I don't know.
They were trying to come up with a use for it for local people, for teens, for education, and
Yeah.
last
Okay.
I heard, nothing was coming from it. So
Yeah. Okay. All right. Now the next one I visited at Mount Wilson Observatory in California, and this is a 150-foot tower, and it's the mirror up here, and there's the light beam going all the way down here. Now, there's the tour that lets you go in, as you can see, the 150-foot solar telescope, and let the people go in. And this is the guide tour. This is the tour guide. And it only takes few people at a time because it's not a very big place. Then you walk in there, and you can see that it's a small place, and they have projected the image of the plate here. And this is the sun here, and this is all the equipment all around. There's people here, and the guys show this is the size of the sun here. There's some kind of projected up there that just projects this, the light beam, project the sun on the white plate here, and they can study the sun. It's not like we do. We look directly at the sun and so forth. No, that's not how they do. They study the sun here, and you can study the sunspots, and they put, they have equipment here to, to study the light of the beam. This is a white light, and now the next thing that they're going to show, to tell the people how big is the sun compared to the size of Jupiter. Yeah. Now this ball here represents the size of Jupiter, and you can see with respect to the sun, the size of the sun, to tell the people how big is the sun compared to Jupiter, the largest planet in the solar system. And of course, it's very bright here. You got to wear your sunglasses. When they work on it, they wear the sunglasses, and you can see some people have sunglasses there because it's very bright. And I don't know if this kind of overexposed. There were some few sunspot groups here, but hard to see from this angle. So this is the nicest way. You're able to visit. It's open to the public, and you can visit there. If you're in the tour group, and then you have the guy explaining how they do the solar research there. Okay, now, as you know, I'll be in California in a couple of weeks, and the second week of September. I'll be in the Southern California area, but I have a day to visit the Big Bear Solar Observatory in Big Bear. It's about almost 2 hours away from Los Angeles, more inland. And there's a solar observatory being built in the middle of the lake, Big Bear Lake. And they have like a pathway, and it's a long pathway, and it made like a man-made island almost in the middle of the lake. Now, the purpose of that is to eliminate the disturbance, atmosphere disturbance around the telescope, and so it can provide better seeing than it will be on land. So, because being that it's surrounded by water, it's a less turbulence there, so the seeing can be much sharper or maybe better than average and all. So I already set up the date to have the tour there. They only can take one group at a time, small group at a time, because it's not a very big place. At the door here, they have 3 floors. They have a lobby here. They have all the equipment here, and there's a telescope here. I think it's 1.6, something like that. But so hopefully, I be part of the tour on that second week of September. And so you got to put your name to it. It only take a few people at a time. It's not a big place. So hopefully I'm able to join the tour group there. Yeah.
You know how long the tour is, Frank?
About an hour and a half. Yeah. So that's